Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence.
Hey everyone! Excited to dive into this week's topic, GIScience in the era of AI. It's a huge area with so much potential.
Indeed, it's certainly a hot topic. I'm interested to see how AI is being applied and whether it's actually solving the right problems or just creating new ones.
I think the real question is, are we actually building intelligent GIS systems or just really good pattern recognition machines? There's a big difference.
Exactly. Let's start by defining GIScience for our listeners. It's essentially the science behind geographic information systems, right? Collecting, analyzing, and visualizing spatial data to understand our world.
Right. Everything from mapping and urban planning to environmental monitoring and disaster response. It's used everywhere, really. And now, AI is being used to automate many of these tasks.
Automating maybe, but is it understanding? That's where I start to get skeptical. You can train a model to identify buildings in satellite imagery, but does it actually know what a building is?
That's precisely my point. A deep learning model can classify land use based on spectral signatures, but does it understand the underlying ecological processes? Can it reason about the impact of deforestation on local climate patterns?
Okay, so let's dig into some specific examples. Otto, you've been looking into how deep learning is being used in GIScience, right? What are some of the most promising applications you've seen?
Absolutely. One of the biggest areas is in image recognition and classification, like we were just mentioning. Deep learning models are incredibly good at identifying objects in satellite imagery and aerial photos. You can automatically map roads, buildings, forests, bodies of water, basically anything you can see in an image.
Yeah, but isn't that just sophisticated pixel matching? I mean, a convolutional neural network is essentially just learning to recognize patterns in pixel arrangements. It doesn't understand the context, the function, or the relationships between those objects.
Well, yes and no. It's true that it's based on pattern recognition, but the models are getting more and more sophisticated. They're starting to incorporate things like attention mechanisms, which allow them to focus on the most relevant parts of an image. And they're being trained on massive datasets, which allows them to learn more complex and nuanced patterns.
But even with attention mechanisms and massive datasets, it's still fundamentally a brute force approach. You're essentially throwing data at the problem until the model learns to recognize the patterns. There's no real understanding of the underlying spatial relationships.
Right. I think a key question is, how can we move beyond just pattern recognition and build AI models that can actually reason about space and time? I mean, one area I've been looking at is how the brain processes spatial information. Neuroscience offers some interesting clues.
That's interesting. What kind of clues?
Well, for example, the hippocampus is crucial for spatial navigation and memory. It uses things like place cells and grid cells to create a cognitive map of the environment. Now, how can we translate those principles into AI algorithms? Can we build AI models that create similar internal representations of space?
That's where neuro-symbolic AI comes in, right? Combining the strengths of neural networks with symbolic reasoning. Instead of just learning patterns from data, you explicitly encode spatial knowledge and rules into the system. For example, you could define rules about topological relationships. Things like a river always flows downhill or a city is typically located near a water source.
But isn't that incredibly complex and difficult to implement? I mean, you'd have to manually encode all that knowledge, and it would be very brittle and hard to generalize to new situations.
I think the challenge is not just encoding the knowledge, but also representing it in a way that the AI can actually use it. You need a representation that can handle uncertainty, ambiguity, and scale. And it needs to be able to translate between different coordinate systems.
Yeah, the coordinate transformation is a big one. Think about how we use different maps at different scales. A city map uses a different projection and level of detail than a world map. How can an AI model seamlessly switch between these different representations and still understand the underlying spatial relationships?
That's true. I mean, even with deep learning, you can train separate models for different scales, but they wouldn't be able to share information or generalize to new scales very well.
Exactly. That's why I think we need to move beyond purely data-driven approaches and incorporate more symbolic reasoning. You need a system that understands the underlying mathematical mappings between different coordinate systems. It needs to know how to project a sphere onto a plane and how to account for distortion.
And it needs to be able to handle temporal transformations as well. How does the spatial information change over time? How do you represent the movement of a hurricane, the growth of a city, or the shifting of tectonic plates?
Which brings us to the concept of spatiotemporal reasoning. Thinking about space and time together is crucial for understanding many real-world phenomena. For example, predicting traffic patterns requires understanding not just the road network, but also the time of day, the weather, and any special events that might be happening.
That's where I think deep learning can still play a significant role. Recurrent neural networks like LSTMs are specifically designed to handle sequential data. You can feed them time series data of traffic flow and train them to predict future traffic patterns.
But again, that's just pattern recognition. It's not understanding why the traffic patterns are changing. It doesn't know about the underlying causes, like accidents, construction, or increased demand.
I think the key is to combine the strengths of both approaches. Use deep learning to extract features from the data, but then use symbolic reasoning to interpret those features and make inferences about the underlying processes. It's a hybrid approach.
A hybrid approach sounds promising. Maybe we can use deep learning to learn low-level spatial features, like edges and corners, and then use symbolic AI to build higher-level representations, like buildings, roads, and forests. The AI could then reason about the relationships between these objects and make inferences about the spatial environment.
That makes sense. It's like using deep learning as a preprocessor for symbolic AI. But wouldn't that still require a lot of manual engineering to design the symbolic reasoning component?
Potentially. But there are ways to automate that process as well. You can use techniques like inductive logic programming to automatically learn rules from data. You start with a set of background knowledge and a set of examples, and the algorithm learns a set of rules that explain the examples in terms of the background knowledge.
The other aspect I would add to this equation is coordinate reference system and how the system is able to translate the data. Most models currently need the data to be reprojected into one coordinate reference system. I am interested in AI being able to understand these translations between coordinate systems to better reason about the Earth.
That's fascinating, Donald. It brings to mind this recent research I read about called infinite ICL. It's all about expanding the context window in AI models, allowing them to process and reason about much larger amounts of information. Think of it as giving the AI a much longer memory.
Infinite ICL? I've heard rumblings. Sounds like they are tackling context window limitations by scaling up. How does that even work?
If it doesn't address spatiotemporal context and the underlying coordinate transformations, then I agree with Sarah. More data, same problem.
Okay, fair points. But consider this. If the AI can access and process a much larger amount of spatial and temporal data, could it potentially learn those underlying relationships and transformations on its own? Maybe the brute force approach is enough if you have enough data.
That's the deep learning dream, right? That with enough data and enough compute, you can learn anything. The promise of AGI through scaling.
You need a way to represent that knowledge in a way that's flexible and adaptable. I think the key is to develop algorithms that can translate between different levels of abstraction, from raw sensor data to high-level concepts.
So, let's bring it back to infinite ICL. If this technique can truly expand the context window, what are the potential implications for GIScience? Could it allow AI models to reason about much larger spatial regions, to understand the complex interactions between different ecosystems, or to predict the long-term impacts of climate change?
Potentially. Imagine an AI that can analyze decades of satellite imagery, weather data, and economic indicators to predict future land use patterns. You could use that to optimize urban planning, to protect endangered species, or to mitigate the effects of natural disasters. Infinite ICL could really unlock the insights.
But what about the biases in the data? What if the satellite imagery is of poor quality, or the weather data is incomplete, or the economic indicators are misleading? Will the AI just perpetuate those biases, or will it be able to identify and correct them?
And what about the ethical implications? Who gets to decide how this technology is used? Who benefits from it and who gets left behind? We need to think carefully about the social and political consequences of AI and GIScience.
Those are crucial questions. Absolutely. We need to ensure that AI is used responsibly and ethically, and that it benefits all of humanity. So maybe instead of just thinking about the potential benefits of infinite ICL, we should also be thinking about the potential risks and how to mitigate them.
I agree. And I think it's important to remember that AI is just a tool. It's not a magic bullet. It can help us solve complex problems, but it's not going to solve them for us. We still need human expertise and judgment.
Exactly. We need to use AI to augment our own abilities, not to replace them. And we need to make sure that we're developing AI systems that are transparent, explainable, and accountable.
So, if we are going to achieve AGI, we need to make it coordinate aware. The most efficient AGI GIS systems will need this translation of coordinates to reason about the Earth better.
Okay, so let's shift gears and talk about future research directions. From each of our perspectives, what are the most promising areas for future exploration in AI and GIScience?
From my perspective, I think the most promising area is in developing more sophisticated deep learning models that can handle spatiotemporal data. I want to see models that can not only recognize patterns, but also reason about the underlying processes that generate those patterns. I'm thinking things like graph neural networks that can model complex relationships between different spatial entities, or transformers that can handle long-range dependencies in time series data.
I think the most promising area is in neuro-symbolic AI. I want to see more research on how to combine the strengths of neural networks with symbolic reasoning. I'm talking about systems that can learn rules from data, reason about uncertainty, and explain their decisions in a human understandable way. I want to see AI that understands what it's doing, not just mimics it.
For me, it's all about spatiotemporal reasoning and coordinate systems. I want to see AI models that can seamlessly translate between different coordinate systems and reason about how spatial information changes over time. I'm thinking about algorithms that can learn the underlying mathematical mappings between different projections, or that can represent the movement of objects in 4 dimensions, 3 spatial dimensions plus time.
From my perspective, I'm really interested in exploring the connections between neuroscience and AI. I think there's a lot we can learn from the brain about how to build more intelligent and efficient AI systems. I'm talking about things like neuromorphic computing, which uses brain-inspired architectures to perform computations, or spiking neural networks, which more closely mimic the way neurons communicate with each other.
Neuromorphic computing is definitely fascinating, but is it really practical? I mean, the hardware is still very expensive and immature.
And spiking neural networks are computationally very expensive. It's not clear that they offer a significant advantage over traditional neural networks.
I think the challenge is not just mimicking the brain, but understanding the principles that underlie its operation. We need to abstract away the biological details and focus on the essential computational mechanisms.
I agree. It's not about building a perfect replica of the brain, but about learning from its design principles. How does the brain represent information? How does it learn? How does it reason? If we can answer those questions, we can build much more intelligent AI systems.
Well, this has been a fascinating discussion. I'm excited to see where AI and GIScience are heading in the future. It's a field with enormous potential to transform our world.
Indeed. I remain cautiously optimistic, but I think we need to be mindful of the potential risks and ethical implications.
And we need to focus on building AI systems that truly understand the world, not just mimic it.
Thanks for joining us on Cognitive Spirals. Until next time, keep exploring.